Power is the backbone of any electronic system, and the power supply is what feeds it. Choosing the right supply can make the critical difference between optimum performance and inconsistent results. Let's first cover some AC/DC fundamentals. Alternating current is generated by electrons flowing in alternating directions. Direct current is generated by electrons flowing in only one direction. AC is also called mains electricity, household current, domestic power, line power, or wall power because it is the voltage supplied by a wall outlet. Worldwide, AC voltages range from 100 to 240 volts. The two most common frequencies are 50 Hz and 60 Hz, which designates the rate of direction change per second. The units designed to use AC, such as motorized equipment like refrigerators, tend to require large amounts of voltage, so the voltage is not stepped down as frequently as equipment using DC. Most smaller electronic devices, such as laptops and household gadgets, require direct current to operate with an AC to DC converter from wall power. DC allows for a constant flow of current. Since AC is delivered initially, power must first be converted from AC to DC. Which type of current to use depends on what the load is. In addition to alternating current AC to direct current DC power supplies, DC to DC converters are also available. While both AC and DC can shock you, AC is by far the greater risk because the current capacity is so much greater. Be sure that all electrical equipment that accesses the AC mains uses a circuit breaker or GFCI. Alternating current takes the form of a sinusoidal wave, with the voltage alternating from positive to negative over time. In the first step of conversion, the voltage is rectified using a set of diodes. Rectification transforms the sinusoidal AC into a series of positive peaks. Once the voltage has been rectified, there is still fluctuation in the waveform, the time between the peaks, which must be removed. The rectified AC voltage is then filtered or smoothed with a capacitor. The capacitor is typically quite large and creates a reservoir of energy that is supplied to the load when the rectified voltage drops. The incoming energy is stored in the capacitor on the rising edge and expended when the voltage falls. This significantly reduces the amount of voltage droop and smooths out the voltage. Increasing the storage capacity of the capacitor generally produces a higher quality power supply. Once the voltage conversion is complete, there is still some variation in output, called ripple. In a regulated power supply, the voltage is then passed through a regulator to create a fixed DC output with less ripple. Direct current power supplies are either unregulated or regulated. Unregulated is the most basic type of power supply and does not have the ability to support consistent voltage to a load, while regulated power supplies do. Regulated supplies come in several options including linear, switching, and battery-based. Because unregulated power supplies do not have voltage regulators built into them, they are typically designed to produce a specific voltage at a specific maximum output current. The most common power adapter is nicknamed a wall wart and used to turn AC into a small trickle of DC. A power supply takes the AC from the wall outlet, reduces the voltage using an input transformer, typically stepping it down to the voltage required by the load, and converts it to unregulated DC. For safety reasons, the transformer also separates the output power supply from the mains input. An unregulated DC power supply typically consists of rectifier and capacitor smoothing, but no regulation to steady the voltage. It may have safety circuits and would be best for applications that do not require precision. The DC voltage output is dependent on an internal voltage reduction transformer and should be matched as closely as possible to the current required by the load. Typically, the output voltage will decrease as the current output to the load increases. The advantages of unregulated power supplies are that they are durable and can be inexpensive. They are best used, however, when precision is not a requirement, as they have a residual ripple. Wavelength does not recommend using unregulated power supplies with any of our products. A regulated DC power supply is essentially an unregulated power supply with the addition of a voltage regulator. This allows the voltage to stay stable regardless of the amount of current consumed by the load, provided the predefined limits are not exceeded. In regulated power supplies, a circuit continually samples a portion of the output voltage and adjusts the system to keep the output voltage at the required value. In many cases, additional circuitry is included to provide current or voltage limits, noise filtering, and output adjustments. Of the three basic regulated power supply designs, linear is the least complicated system. Linear power supplies are used when precise regulation and the removal of noise is most important. While they are not the most efficient power source, they provide the best performance. The name is derived from the fact that they do not use a switch to regulate the voltage output. Linear power supplies have been available for years, and their use is widespread and reliable. The disadvantage to linear power supplies is that they require larger components, hence are larger and dissipate more heat than switching power supplies. Compared to switching power supplies and batteries, they are also less efficient, sometimes exhibiting only 50% efficiency. Switching power supplies are more complicated to construct, but have greater versatility and polarity, and if designed properly, can have an efficiency of 80% or more. They typically have a wide input voltage range and a higher output current range. Although they have more components, they are smaller and less expensive than linear power supplies. Because switching power supplies operate at higher frequencies, they can radiate noise and interfere with other circuits. Interference suppression measures, such as shielding and following layout protocols, must be taken. Battery-based power is essentially a mobile energy storage unit. They produce negligible noise to interfere with the electronics, but lose capacity and do not provide constant voltage as they drain. With batteries, it is often difficult to match the correct voltage to the load. Using a battery that can exceed the internal power dissipation of the driver or controller can also damage the device. When choosing a power supply, there are several requirements that need to be considered. The power requirements of the load or circuit, including voltage and current. Safety features to protect the load, such as voltage and current limits, load regulation, overvoltage, and overload protection. Physical size and efficiency. Noise immunity of the system. Load regulation is how well the regulator can maintain its output with a load current change, and usually is measured in millivolts or as a percentage of maximum output voltage. Sometimes output voltages can exceed their nominal values and can damage the load. Overvoltage protection is a circuit that shuts down the power supply should the voltage limits be exceeded. Overload protection is a safety measure used to prevent damage in the event of a short circuit or overcurrent event. Much like the circuit breaker in a house, the overload protection shuts off the power supply so the load will not be damaged. Efficiency is the ratio of power being pulled from the power grid to that effectively being converted to DC power. An efficient system will reduce heat generation and can save energy. Noise and ripple are artifacts of the transformation of AC to DC and are the byproduct of rectification and switching. During conversion, the alternating sine wave cannot be completely suppressed. These artifacts are typically combined into one specification given in peak-to-peak voltage, showing the extent of the noise spikes that arise from switching, which can negatively affect sensitive instrumentation. The small voltage variations are called ripple. Many times, the amount of fluctuation depends on how well the power supply is matched to the load. Noise is the unwanted additions that occur outside of the normal ripple and is much more variable and unpredictable. It comes from many other sources, including electronic noise generated from nearby equipment. Switching noise typically occurs at very high frequencies. The noise potential in a regulated linear power supply, while much less than the ripple of a regulated switching supply, can still be significant enough to mask data. If the noise and ripple are very high, small signals can be overwhelmed or the life of the hardware can be significantly shortened. However, with a high-quality power supply, it can be virtually eliminated. Along with the above considerations, the power supply must operate below its maximum rated output current. Loads drawing more current than the adapter is rated for can cause inconsistent results or device malfunction. Overloading the converter can lead to overheating and ultimate failure, potentially causing a fire hazard or damaging the load itself. How much current does my power supply need? A good rule of thumb is to combine the amount of drive current needed to meet the needs of the load and the current needed to power the controllers, and then add 10% as a buffer. Can I use the same power supply to drive my temperature and laser controllers? Yes, as long as the voltage selected meets the needs of the load and is within the safe operating area of the controller, and the laser thermoelectric and temperature sensor are not electrically tied through ground. For more information on SOA, see the application note on our website. There is also an application note on grounding. Can I use the same power supply to drive several temperature controllers at the same time? Yes, but they should be connected using star, individual connections, rather than serial, linked connections to ensure that the voltage to each unit is the same. How long should my cables be? Longer cables introduce more noise and allow for more voltage drop between the power source and the load. To minimize the effects of noise, twist the cables together or use shielded cables. To help minimize voltage drop, keep them as short as possible. What gauge wire should I use? The gauge determines the current carrying capacity and needs to exceed the specification of the load. For example, this table shows some standard gauges and carrying capacities. A 20 gauge wire, not a 22 gauge wire, would be required for a load of 2 amps. This is because the 20 gauge wire allows a 3.2 amp current, which exceeds the 2 amp requirement. For more answers to frequently asked questions and some historical background, go to our website basics page. Consider us an extension of your team.